Greetings, tech aficionados. It's your coding maestro, Big Papa Code, here to guide you on another thrilling escapade into the universe of coding. Today's quest, diving deep into the realm of big O, time, and space complexity. Strap in, for it's going to be a wild, wondrous journey through the nuances of algorithm efficiency. Have you ever pondered why some programs run at the speed of a sprinting cheetah, while others lag behind like a leisurely snail? What's the secret sauce that dictates the pace? Picture a kitchen. On one end, you have Chef A, methodical, organized, with every ingredient and tool in its place. On the other, Chef B, frantic, disorganized, forever searching for that elusive salt shaker. Who do you think will whip up a dish faster and more efficiently? It's not just about having the right ingredients. It's about how you utilize them. Similarly, in the world of algorithms, it's not just about solving a problem, but how efficiently you solve it. Enter Big O notation, our mathematical metric to describe the performance and complexity of algorithms. Think of it as the recipe's cooking time. It gives you an upper bound on the time taken, helping you anticipate the worst-case scenario. While time complexity gauges the amount of time an algorithm takes to run, space complexity measures the memory it uses. Together, they form the crux of optimal programming. Just as in our kitchen, it's pivotal to be both fast, time efficient, and resourceful, space efficient. So just as Chef A's methodical approach ensures a dish is prepared efficiently, understanding Big O notation ensures our algorithms run optimally. Whether in the kitchen or coding, the principles remain: organization, efficiency, and mastery over tools and ingredients, or in our case, code. Constant time. No matter how much data you have, the algorithm takes a consistent amount of time to complete. Think of it as turning on a light switch. It takes the same amount of time regardless of the room's size. Logarithmic time. In algorithms with this complexity, the number of operations decreases by a factor with each step. Binary search is a classic example. Imagine you're looking for a word in a dictionary. Instead of checking every word, you open the dictionary to the middle, see if your word would lie in the first half or the second half, and then repeat the process on that half. You keep dividing the dictionary in half until you find your word, or you've checked enough to know it's not there. This is much quicker than checking every word one by one. Linear time. The time it takes for the algorithm to complete is directly proportional to the amount of data. For instance, if you're searching for a specific item in an unsorted list by checking each item one by one, the time taken grows linearly as the list size increases. Quadratic time. The time it takes is proportional to the square of the amount of data. For algorithms with this complexity, as the input grows, the time taken grows much more rapidly. An example is the bubble sort, where for each element, you might need to compare it to almost every other element. In essence, when choosing algorithms, understanding these complexities helps pick the most efficient one for the task at hand. Apply the same thinking to space complexity as well. Constant space. No matter the input size, the space used remains constant. Linear space, the space taken up grows proportional to the input size. Logarithmic space complexity indicates that the memory usage grows logarithmically with the input size, often seen in recursive algorithms where each call reduces the problem size. Quadratic space is where the space usage increases in proportion to the square of the input size. Understanding Big O time and space complexity isn't merely academic, it's practical. It's the difference between a traffic system that prevents jams and one that causes them. A game that processes inputs in real time versus one that always lags. A search engine that delivers instantaneous results versus one that leaves you waiting. In essence, it's the backbone of efficient, effective software design. And in today's fast-paced tech universe, efficiency isn't just desired, it's demanded. And there we have it, dear tech enthusiasts. A whirlwind journey through the peaks and valleys of Big O time and space complexity. Feeling enlightened? If this digital dive added a bite of knowledge to your coding repertoire, then hit that like button. And if you haven't subscribed yet, what are you waiting for? Join the Big Papa Code fam, and let's keep exploring this vast digital cosmos together. Until next time, keep those brackets in line, and may your code be ever bug-free. P.S. Don't forget to check out me and my friends on the Deeper Than Code podcast, available on YouTube and Spotify. Peace.